Welcome to this explainer. Today, we're diving into what I like to call the ultimate atomic detective story. We're going to find out exactly how early chemists and physicists managed to map the invisible layers of the atom long before we had microscopes powerful enough to even dream of seeing them. So here's the fundamental question. How exactly do we measure an atom's invisible grip on its electrons when we can't even see them? It's brilliant, actually. To figure out this hidden subatomic architecture, we essentially have to play a cosmic game of tug-of-war. We measure exactly how hard it is to steal an electron away from the nucleus. Part 1. The electron tug-of-war. All right, so the crucial starting point is our formal definition for this initial battle, known as the first ionization energy. It's simply the energy required when 1 mole of gaseous atoms forms 1 mole of gaseous ions with a single positive charge. And, note that specific detail. It always happens in a gaseous state, like a gas atom turning into a positive gas ion, leaving us with a loose electron. What this means is the whole process is always a positive endothermic battle. We are literally fighting against the natural electrostatic pull between that positive nucleus and the negative electron. So this always requires us to supply energy. The atom isn't just going to hand over its electron willingly, right? Moving on to part 2, the 3 rules of attraction. Every single atomic mystery we're unpacking today basically boils down to these 3 simple rules. 1, the attraction of the nucleus, so the number of protons. 2, the distance of the electrons from the nucleus, basically the atomic radius. And 3, the shielding effect. This is when those inner, fully packed shells of electrons run interference, pushing back on the outer electrons and weakening the nucleus's overall grip. That brings us to part 3. Clue number 1, successive energies reveal shells. Now think about what happens when we go in for a second electron. As we remove it from an already positive ion, the atom's grip tightens dramatically. Because you're now pulling a negative charge away from something that's already positively charged, successive ionization energies for any element are always going to be larger than the previous one. Take a look at the raw data for this mystery element. Do you notice anything a little suspicious about how the required energy jumps? I mean, the first takes 590 kilojoules per mole. The second takes 1150. That's a jump, sure. But then look at the third, a whopping 4,940. Plotting this data out reveals our very first major clue. That massive sudden spike you see between the second and third ionization energy, that proves something structural. It literally proves we just tried to break into a brand new, unshielded inner shell of electrons sitting way closer to the nucleus. So, because it only had 2 easily removable outer electrons before we hit that absolute brick wall of energy, we've successfully deduced who this mystery element is. It has to live in group 2 of the periodic table. Think about that. Just by measuring shear force, we are literally mapping out where these electrons live. Part 4. Clue number 2, the group trend. Now, as we move down a group on the periodic table, the first ionization energy actually drops. Why? Well, going down a group means we're adding entirely new main electron shells. This pushes those outermost electrons much further away from the nucleus, which massively increases that shielding effect we talked about earlier. This gives us a perfect contrast. On one hand, you have a tiny element like helium guarding its electrons like a dragon hoarding gold because it has 0 inner shielding. Contrast that with a massive atom like rubidium. Its outer electrons are so heavily shielded by all those inner shells and sitting so far away that they barely feel the nuclear pull at all. It makes them super easy to pick off. Which leads us to part 5. Clue number 3, period trends and subshell secrets. Let's see how this plays out across period 3. Generally speaking, the energy required increases from left to right. This makes sense because we're adding more protons to the nucleus without adding any new shielding shells. But if you look really closely at the data from magnesium to aluminum, and then again from phosphorus to sulfur, there are these sudden, completely unexpected dips. Anomalies in the data. I mean, why on earth do aluminum and sulfur suddenly lose their grip? Well, these tiny drops in the general trend are actually our final and honestly most exciting clues. They give us hard physical evidence for hidden sub-energy levels existing right inside the main shells. Let's take that first step. Aluminum actually has more protons than magnesium, so based on our earlier rules, it really should be harder to steal an electron from it, and yet the energy required actually drops, going from 736 down to 577 kilojoules per mole. The explanation for this anomaly is beautifully simple. Aluminum's outermost electron has just started filling a slightly higher energy 3p subshell. Because it's in this new 3p space, it gets slightly shielded by the electrons sitting in the 3 subshell right below it. And that tiny extra bit of shielding, that's what makes it easier to remove. But you might be wondering, what about that second anomaly, the drop from phosphorus to sulfur? Both of these elements are filling that exact same 3p subshell we just talked about. So what causes sulfur to suddenly lose its pulling power? The answer here lies in electron arrangement. In sulfur, the fourth 3p electron is actually forced to pair up in a single orbital box. Now, because two negative electrons naturally repel each other when they're crammed into the same tight space, that slight repulsion, that extra outward push, makes it significantly easier for us to just pluck one of them away. And finally, part 6, the invisible map revealed. To sum this all up, the dry data of ionization energy isn't just a list of random numbers. It's literal forensic evidence. It proves that the main electron shells exist, it proves hidden subshells exist, and it shows how the basic rules of electrostatic attraction, protons, distance, and shielding really do govern our universe. Which leaves us with a truly fascinating thought to end on. If we can deduce the highly complex, invisible layout of an atom simply by stealing its electrons, what other unseen worlds can we map through sheer scientific deduction? It really makes you wonder, doesn't it? What other invisible structures are hiding all around us, just waiting for the right scientific detective to come along and measure them? Thanks for joining me on this explainer, and I hope you walk away seeing the atomic world just a little bit clearer.